back. We are going to start a new unit, learning about chemical reactions and quantities. For this video, the learning goal is to be able to write a balanced chemical equation from the formulas of the reactants and products for a reaction. And you'll also be able to determine the number of atoms in the reactants and products. And so just a reminder, a chemical change, we've learned this before in a previous video, occurs when a substance is converted into one or more new substances that have different formulas and properties. We see this, for example, when we have iron nails. Over time, the iron in the nails reacts with oxygen in the air, and that produces rust, which is iron 3 oxide. For this unit, there are some core math skills you will need to utilize, such as calculating a percentage, solving equations. We'll use a lot of dimensional analysis in this unit, and then writing numbers in scientific notation. Some of the core chemistry skills that you will need is counting significant figures, using significant figures in calculations, writing conversion factors from equalities, using those conversion factors in dimensional analysis, using energy units, writing ionic formulas, naming ionic compounds, and writing the names and formulas for molecular compounds. So once again, a chemical change occurs when a substance is converted into one or more substances with different formulas and different properties. It may be observed in the laboratory by the formation of bubbles, or maybe a color change, or the production of a solid, a precipitate in your test tube, or heat that's produced or absorbed. Here's another example. If you have silverware that's made of silver, or even jewelry that's made of silver, then it can tarnish over time to form silver sulfide. And so when you see, for example, a substance change formulas, then a chemical change has occurred to produce the new substance. So when we write a chemical equation, we will have the reactants on the left side of the arrow and the product or products on the right side of the arrow. And so you may have one reactant or more than one reactant. You may have one product or more than one product, just depends what you're working with. And as you can see, once again, the identity of the substances changes. So that's when a chemical reaction occurs. It's not like, for example, a physical property changing or a physical change like we saw, for example, when we boil water. And so we saw this in a previous video where I used similar notation where I had water here in the liquid phase. And then when we're evaporating it, it's undergoing vaporization, it turns into gas. But notice how the identity of the substance stays the same. And so this is a physical change, not a chemical change. So to write a chemical equation, once again, an arrow separates the reactants from the products. So this arrow here separates the two. Reactants on the left, products on the right. So anytime you hear me use those words like reactants, you're going to visualize, oh, they're on the left side of the arrow. If I'm referring to the products, then you're like, oh, that's on the right side of the arrow. So that's part of our vocabulary here. And if you have multiple reactants and or multiple products, they're always separated by a plus sign. And if you ever see a delta, like the Greek symbol delta here, it indicates heat is used to start the reaction. So sometimes reactions need a little bit of heat energy to get them started. And so therefore you'll see a delta there to indicate heat. And so what I mean by that is if you're running a chemical reaction that requires heat, you may use a hot water bath. For some of my reactions, In my research, since I did polymerizations, I needed to run them at really high temperatures, like 300 degrees Celsius. So I used an oil bath, or some people would use a sand bath, which gets hotter than a boiling water bath, which is only 100 degrees Celsius. So just to give you some examples of ways you can heat your reactions. Now, we always need to indicate the physical states of compounds in parentheses following the compound. So you've seen me kind of do that throughout these videos. You'll see me keep doing that to stay consistent. I will use S for solid, L for liquid, G for gas, and AQ for aqueous. So whenever you see the word aqueous, that means it's dissolved in water. Here's a summary of the symbols we use in writing equations. Now, due to the law of conservation of mass, no atoms can be lost or gained in a chemical equation. So when we balance them, we are working under the assumption that no atoms are lost or gained. So what that means is that the number of atoms on the reactant side are equal to the number of atoms on the product side for each element. As you can see in this example, we are reacting carbon with oxygen gas to produce carbon dioxide. And you can see here we have one carbon atom on the left side, one carbon on the right, two oxygen atoms on the left, and two oxygen atoms on the right. So this equation is balanced. So here's a guide to balancing chemical equations. You will write the equation using the correct formulas for the reactants and products. What I mean by that is for carbon dioxide, the correct formula is CO2. You will count the atoms of each element in the reactants and products, and you will use what's called coefficients to balance each element. And I will model that in the next example. And then check in the end to see if the final equation is balanced, that the number of atoms on the left for each element is equal to the number of atoms on the right. And this is a core chemistry skill, balancing chemical equations. If this is your first time balancing a chemical equation, it can take some time. So, make sure you practice some patience with yourself. It might take a little while, but with enough practice, you will get faster at it. You will learn your own tricks to solving these balancing chemical equations quicker. I know for me as a student, it took me a while to grasp it at first. But once I practiced more and more problems, I saw patterns. And then once you see these patterns, it gets faster and faster. So let's work an example together. We're going to balance the following chemical equation. We are reacting aluminum with sulfur to produce aluminum sulfide. And so what I like to do with students when you're first learning it, you're not required to do these tables, for example, on your assessments or even on your homework. Although I recommend it once again, if this is your first time balancing equations, to do the table so that you get faster at balancing them. And what I mean by that is I always tell students to write down the elements on the left side and then to count them. So on the left side, I have one aluminum, and on the right side, I have two. So that subscript implies I have two of those aluminum atoms. So I'm going to write two here and only one here. So this is not balanced yet. And then sulfur, I have one here, and I have three sulfurs here. And so what I notice here is that I'm going to start with the aluminum. I have two over here. I want two here. Now I can't write Al2 subscript because that doesn't exist in nature. In its simple elemental form, it's just monoatomic aluminum. But the way you can balance equations is by adding what's called a coefficient out front. And so I'm going to put a 2 in front of this aluminum This is the coefficient that I was referring to in the guidelines. You'll hear me refer to as the stoichiometric coefficient later on as we talk about stoichiometry together. But for right now, we will just call it the coefficient. And by putting that 2 out front, then I now have 2 aluminum atoms and the aluminum is balanced. When I see over here, I have 3. Then what do I need to add in the front of the sulfur? What coefficient? 3 as well. Fantastic. So then now I have 3 sulfur atoms on both sides, so it is balanced as well. So when you're balancing chemical equations, you can only add stoichiometric coefficients. You're never going to add subscripts. Subscripts is when you're predicting that product, for example, correctly, the correct formula. This is aluminum sulfide, it's an ionic compound. If you did the crisscross rule, this is the formula you would come up with, right? But once we've written the equation, in order to balance, we can only add coefficients in the front of our reactants and our products to balance the number of atoms. You never change the subscripts once you've predicted the correct formulas for your reactants and products. All right, so go ahead, pause this video, try the study check on your own, and then check your work with me when you're done. All right, so this study check asks us to state the number of atoms of each element on the reactant side and the product side for the following balanced equations. So these are already balanced. So this is a way for us to kind of practice to see if we can determine the number of atoms correctly. So I'm going to do part A, P4, and then bromine and phosphorus bromide here. And so if I had to count, first I like to just write down phosphorus and bromine. And so how many phosphorus atoms do I have on the reactant side? Good, I have 4. What about on the product side? I also have 4, excellent. How many bromines do I have on the reactant side? 6 times 2 is 12. So when you have, for example, a stoichiometric coefficient and a subscript like we do here, we multiply them because we have 6 of these bromine molecules. So if we drew the Lewis structure for bromine, for example, we have 6 of them swimming in solution. And so each of the molecules has 2 bromines. That's why it's 6 times 2. And how many bromines on the product side? Excellent. So you have 4 times 3. The 3's associate with the bromine. So 4 times 3 is 12. And once again, you can always draw the Lewis structures. That was a core chemistry skill you learned in a previous lecture video. So for example, if you had 4 of these phosphorus tribromines swimming around in solution, and then if there's 4 of them, then there's 4 times 3 bromines, right? So that's where we get the 12 bromine atoms, and then only 4 phosphorus atoms. All right, let's do the next example, B. I'm going to go ahead and erase what we have here so I can write below again. And right now I'm just going to write it as is, the table underneath. We have aluminum, we have iron, and we have oxygen as the different elements in this equation. How many aluminums did you count for the reactant side? 2. And what about for the product? Also 2. So once again, just noticing that that subscript is associated with the aluminum. So there's 2. How many irons on the reactant side? We have 2. And what about for the product? 2. So once again, seeing the stoichiometric coefficients associated with those ions, that's 2 there, subscript, that's 2 ions there, and this iron 3 oxide. And then how many oxygens? 3 and also 3. So you can see here, we have 3 oxygens and 3 oxygens. All right. I'm going to get you started on the study check, and then you can pause the video and balance it. But let's get the chemical equation written first. So it says to balance the chemical equation when solid Fe3O4 reacts with hydrogen gas to produce solid iron and water. And so let's go ahead, and we have this ionic compound here, and it's a solid. So I'm going to do an S next to it. And the key word we can see here is it reacts with hydrogen gas. Now, in a previous lecture video, I went over diatomic molecules that exist in nature, and there's 7 of them. Where they exist as partners, right? There's 2 of them together as opposed to just monoatomic. And so if we look at the periodic table, the diatomic molecules are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And so when you hear hydrogen gas, it is not just monoatomic hydrogen, but rather it's diatomic because that's how it exists in nature. So when our ionic compound here, Fe3O4, reacts with hydrogen gas, it's not reacting with just a hydrogen atom, but H2. And then the second keyword to know when to draw the arrow is when you see to produce. So to produce, you would draw an arrow to indicate, okay, now I'm forming my products here. And one of the products is solid iron. Now, iron is not part of the diatomic molecules, so you can assume it's monoatomic. And when I mean by monoatomic, you just write 1, there's no subscript, and it's solid. And water, which we know to be H2O, and we'll just assume that water is a liquid. Now, there are some cases where water will be a gas or it could be a solid, but if it doesn't state, we can assume liquid here for working maybe, for example, at room temperature. And so this is the chemical equation that's not balanced. This is each substance, you know, in its own chemical formula, right here. And now we have to balance it. So now this is where you want to pause the video, try to balance the equation on your own, and then check your work with me when you're done. All right, so I'm going to go ahead and do the table. Like I said, this is how I learned how to balance chemical equations efficiently. So the first thing I like to do is just count the atoms on the left and right. And I see that I have 3 irons on the left, only 1 iron on the right. Oxygens, it looks like I have 4 on the left and only 1 on the right. Hydrogens, I have 2 and 2. And notice, like, I'm writing below the substance that contains the element. It's not required. Some students just write them all in one row, or one in column, that's fine. This just helps me keep track of the different atoms and where they're located in the different chemical formulas. So I'm going to start with iron. I have 3 irons on the left. So what coefficient do you want to add to the right to balance it? Good, you should add a 3 in front. Remember, we can only add coefficients. So iron balances out. Oxygen, I have 4 on the left. So what coefficient do you want to add to the right? Good. So you want to add 4 to the right here. And that will give me 4 oxygens, and that balances out. But you may be like, wait a second, that changes also the number of hydrogens. And that happens when you add a coefficient in front of a molecule that has more than one element, it's going to change the number of atoms for all the elements in that molecule. So not only now do we have 4 oxygens, but how many hydrogens do we have? We have 8. Because 4 times 2 is 8. And so with that being said, if we have 8 over here and we have 2 over here, what coefficient do you want to add in order to balance the hydrogen atoms? Excellent. You want to add 4 because 4 times 2 is 8. So this is where the table is really handy because you can keep track of, how things change as you start adding coefficients. In the previous lecture video, we learned about polyatomic ions, and which are a group of atoms that have an overall charge. You can see here, we will learn in a later lecture video how to predict products of reactions that might have a precipitate and an ionic compound crash out. So I was just showing this here. So we'll learn more about that later. So you'll have a chance to work with polyatomic ions in those videos. So I want to get us practicing it now so you feel comfortable balancing these types of equations. Like I said, this will be a core chemistry skill that will be useful later on. So for example, we have this equation here, and this is sodium phosphate plus magnesium chloride to produce magnesium phosphate plus sodium chloride. And this is what I mean. It produces a solid substance as a product. So that was that precipitate you saw in solution. And we'll learn about how to predict if a precipitate forms or not in a later video. But once again, when we do those types of problems, your knowledge and foundation in balancing these equations will be useful. So when I balance polyatomic ions, I still like to do the table, but to simplify it, what I like to do is I'll write, for example, sodium. I'll keep the polyatomic ion. I'm going to keep the charges because these are all ionic here. So I'm going to keep the polyatomic ion as a group of atoms, as opposed to writing phosphorus and oxygen separate. You could write phosphorus and oxygen separate in your list of atoms, but it will just take longer. So if you notice that you have polyatomic ions in your equation, then and you're balancing them and you're making the table, then keep the polyatomic ions as the group of atoms. And this will help save you some time. This is a trick. So here are the ions that we're working with: sodium, phosphate, magnesium, and chlorine here, chloride. And so now I'm going to write down the number of sodium ions. I have 3 on the left side, only 1 on the right. How many phosphates do we have on the left? We have 1 phosphate, so it's just 1 PO4. If there was more than 1, it would have parentheses and a subscript 2 or greater. On the right, how many do we have? We see it there. We have 2. So that 2 is associated with that whole phosphate group. What about magnesium? We have 1 on the left, and how many on the right? 3. And chlorines, how many on the left? 2. And how many on the right? 1. So let's start with sodium. What coefficient would you add to balance it? Good. You add a 3 in front of it. So we can start there. So if we add a 3 in front of it, that would balance out the sodium. All right, what about the phosphates? It looks like we would need to add 2 in front of here. Remember, we can only add a coefficient in front of the entire compound formula, the molecular formula there. And so 2 would make the whole phosphate 2, which is good. But what does it change when we do that? It changes the number of sodium ions here. So now how many sodiums do we have? 6, because 2 times 3 is 6. So like I said, this is why the table is very useful and I highly recommend it. And over here, what do we need to change? We need a 6 in front of there. Good. And so let's go ahead, erase that stoichiometric coefficient. I'm going to put a 6 here and change it to 6. I like to do this like on my notes. I like to cross it out. I don't like to erase. I just like to see how things progress. And then I can check my work when I'm done. Magnesium, I have 1, but I have 3 over here. So it looks like I need what coefficient? A 3 here to balance the magnesium. But that changes the number of chlorines. How many do I have now? 3 times 2 is 6. And so therefore over here, I also have 6, because remember the coefficient goes throughout the entire molecule there. So I have 6 chlorines. So that worked out in the end. So they all worked out. The stoichiometric coefficients for this equation are 2, 3, 1, 6. All right, go ahead, pause the video, balance these equations and list the coefficients in order from reactants to products, and then check your work with me when you're done. All right, the first one we have here, we have the iron 3 oxide plus carbon plus iron and CO2. So I'm actually going to add a page here so we can make our table together. All right, so we have iron, oxygen, and carbon. We have 2 iron on the left, 1 on the right, 3 oxygen on the left, 2 on the right, and 1 carbon and 1 carbon here. And so the first thing I see is iron, there's 2, so I'm gonna try putting a 2 in front of here to balance it. But then what I noticed, this is where the tricks come in as you practice more and more. I noticed here I have 3 oxygens and 2 oxygens here. And the only way I can balance these oxygens is if I make like a multiple of 3 and 2, which would be 6. What I mean by that is if I need to make this 3 into 6 oxygens and this 2 into 6 oxygens, because otherwise it's hard to balance it. You would need to use fractions to do it. So what I mean is, for example, if I wanted to make this 6 oxygens, then what coefficient would I need up front? I would need 2, because 2 times 3 is 6. If I wanted this to be 6 oxygens, then what coefficient would I need up front? I would need 3. So that's what I mean by they're a multiple of 6, right? 2 times 3 is 6. And so that's a trick. A lot of times oxygens will do that. Like you may have an odd number, 3 on one side and 2 on the other side. So then you're like, okay, I just need to get them to 6 and use coefficients that will get me there. And that changes the number of irons here. So now I have 4. And so therefore I need to change the coefficient to 4. And then the carbons now are 3 because we added a coefficient out here. And so therefore I need a 3 here to balance out the carbon. And so the answer here was 2, 3, 4, 3, B. All right, let's do the next one. We have aluminum plus iron 2 oxide gives us iron plus aluminum oxide. And so aluminum, iron, and oxygen. We have 1 and 2 here, 1 and 1, 1 and 3. Looks like the first thing we'll need to do is add a coefficient 2 in front of the aluminum to balance out the aluminum atoms. For the iron, it looks like they're good for right now. We have 1 and 1. For the oxygens, I need to add a 3 here to balance out the 3 oxygens on the right side. But that changes the number of iron atoms. And so that means I need to have a 3 here to balance out the iron. So these stoichiometric coefficients are 2, 3, 3, and 1, which was choice A. Last example, we have aluminum plus sulfuric acid to give us aluminum sulfate. I'm running out of room. Plus hydrogen gas. This is AQ. All right, so aluminum, hydrogen, sulfate, and I'm going to keep that polyatomic ion together just to save us time. And here we go. We have 1 aluminum, 2 here. Hydrogen, we have 2 and 2. And sulfate, we have 1 and we have 3. So the first thing I'm going to do is put a coefficient 2 out in front of the aluminum to balance that one out. For hydrogen, it looks good for right now. And for sulfate, looks like I'll need to put a 3 out front to balance out the sulfates. But then that changes the number of hydrogens, which is 6. The 3 times 2 is 6. So what do I need up front here? I need a 3 up here to make that into 6. So the coefficients is 2, 3, 1, 3, which is answer choice B. All right, thank you for watching. And as always, email me with any questions.